We are live, week 13, day 2. So you should be able to take the midterm right after this class gets out. There is a window of 24 hours from today to tomorrow to take it. Once you start it, you have 2 hours to finish. That includes the programming assignments on the server. Yeah, go for it. Can you bring the sandwich in here?
Sure.
Thanks. Might be a bad idea, but we'll see. Alright, so where is the midterm? Spring 2021. It's 20 questions, 16 questions technically. One of them is worth more than 1 point. I think this midterm's a little bit easier than the ones in the past. Not a lot of redundancy, a few bitwise questions, some conceptual things about superscalar and pipelining, and I think there's like one question on dependencies of instructions, and there is a pipelining question, so make sure you understand how pipelining works. That one might get you. That one's worth 4 points. And then there's a little debugging thing. What's wrong with this? Right here. No? Okay. What's wrong with this code kind of thing. Alright, so related news, my internet connection has been fixed. AT&T came out and they spliced it together yesterday, and then today they came out and put a permanent fix on it. They were able to splice it pretty quickly. Like I said, there wasn't a lot of slack on the one end of it, and they didn't want to go digging it up to get more slack, so it's kind of tight in there. So they're like, whenever you rebury it, just make sure you don't smash it again. But yeah, they spliced it together pretty quickly, and then they put the permanent fix in today. They're not gonna send out a dig team, and they're not gonna put in fiber optic, which is what I was really hoping for. I was really hoping they would, well, we got to do a whole new run, so we'll just pull some fiber. No, unfortunately not. Unfortunately not. AT&T does not care about the fiber optic. It's the year 2021. When I was in college, we were supposed to be getting fiber optic. Do you guys know about this? Like, they were digging up the streets all over the world. Like, right alongside a sidewalk, you'd see these teams by, Pac Bell digging up the streets, and they were laying fiber everywhere, and we're supposed to have fiber in the home. Man, that just didn't materialize, did it? The government gave billions of dollars of subsidies to all the Bell companies, and so they ended up instead running fiber to the feeder. So your box, I think, has fiber at it, and then at least hopefully it does, and then they'll run copper wires, like they got severed the rest way to your house, and they call that high-speed internet, like we're living in a third world country or something. Although, to be fair, most third world countries have better internet than us. Actually, it's a bit of an exaggeration, but yeah. America is fairly backwards in it. Probably have hundreds of dead fiber in the crosswalks on the street, but they don't care. Yeah. My bandwidth. Give me my bandwidth, my precious. My precious. Yeah. Okay, so, so the server, there are 2 folders in your, it's already on the Raspberry Pi, so the Raspberry Pi is back up right now. I announced that last night. If I become Hazelton, you can see that there are 2 folders there. There's Midterm 45C and Midterm 45E. You might ask what happened to Midterm 45D, and the answer is I didn't get it done, so I just used an older one. So do those 2, C and E. Right. Don't edit them. Don't look at them. Remember, I can see when you look at these things, so don't even look at them until you start the midterm. Okay, so that is a midterm 45 common era. Yeah. Yeah. So don't. Yeah. You may be tempted. What's in the box? What's in the box? But don't look until you've started the midterm on Canvas. Then you can go ahead and take a look at it. They're not too bad. Midterm 45C is, I think, just rewriting a couple functions from C into assembly that aren't too bad. It's a little bit of algebra, like not bad. What's in the box? Yes, good. And then what is 45E anyway? That's an old one. Oh yeah, it's not too bad. It's an array. So midterm 45E is reading and writing to an array, and really simple for loop over an array. Okay, so pretty. If you don't remember how to read and write to an array, now's the time to check, because yeah, they're worth points. They're worth points. All right. Any questions about the midterm? Pretty good. Yeah. I think this midterm is a little bit easier than the practice midterms I gave you. So, yeah, I'll just do the practice midterms, get warmed up for it, and then start it. Okay, so let's see. The Pi was, as you are aware, down for a big chunk of spring break, and then again when the internet connection got severed. So I put the power of choosing the deadline in Reed's hands, and Reed didn't pick a date, but Cabot did. Not really sure how that happened. So anyhow, Cabot picked a date of Saturday at midnight, so your homework is now due at Saturday at midnight. Okay? So it's on Canvas. Okay. And then we will do the next homework assignment, I guess, starting on next Tuesday. It's fine. We got time left in the semester. We actually have a surprising amount of time because we're not doing any projects this year. I ran all of the boxes of stuff over to campus, and it's actually all the Raspberry Pis are over at the school right now. Still rusty on pipelining. Yeah, you probably want to. Yeah. All right, let's do a little bit on pipelining then. It's probably a good idea. Dad jokes. All right, new page. 4, 8. Going. All right. And then I'll redo a little bit of the lecture last time on memory maps, because the laptop won't record the screen. I don't know why. It might be because it has a separate GPU for the CPU and the dedicated card. I don't know, but it couldn't capture the screen, so it only captured the PowerPoint presentation. So I'll probably redo a little bit of that. Anyway, let's talk about pipeline. So let's say that you've got these instructions: add R0, R1, R2, add R3, R0, R0. What kind of dependency is this? Remember, there's 4 possibilities, right, for a dependency: read after read, read after write, write after read, and write after write. Okay. So this is doing a read after a write, so this is the bad one. Remember, raw is war, right? Wait, no, it's WWF. Yeah, so that's a read after write dependency, and so this is going to cause a pipeline stall. What's going on, Tristan? Good to see you, man. Tristan, are you free on Sunday by any chance? It's going to cause cause a stall. Stall. Okay. Yeah, I'm fully vaccinated now, so I'm ready to just see people again. All right, so the how much of a stall this creates depends on the details of the pipeline. You just kind of have to look at it. On the midterm, it'll tell you, right? So perhaps if this guy enters on cycle 0, then this guy, you know, there's going to be a certain pipeline depth. Let's say that this guy finishes on cycle 10, then this guy will enter on cycle 11. Okay. And then if we have another thing like this, add R4, 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 then this would enter, if you're not doing out of order execution, this would enter on cycle 12. If you had out of order execution going on, then this would slide up into there. Okay. So, but for the example in the midterm, there's no out of order execution, so it's just, you just straight down, no superscalar, no out of order. You just try to figure out where the stalls are. Okay. And so the instructions will tell you how big this delay is, right? And yeah, that's about it. So if there was out of order execution, I was thinking about it, some of the midterm questions in the past, I had you guys figure out where to put this instruction. I didn't do it on this one. Like I said, I made it kind of easy. There's a conceptual question about out of order execution. So you need to know what it is. You need to know what speculative execution is. Do you guys know what speculative execution is? Specs. You guys remember that? Do you remember out of order execution? Super scale. It's not called SS. Super scalar. And then there's speculative execution, out of order execution, pipelining. What else do we do? Registry naming. Can you go over speculative execution? Sure. Okay. So let's say that you got a loop. So you got this command here, add R0, R1, R2. You got a branch, add and set, let's say. So branch if it's not equal to 0 to A, otherwise do an add of R0 and 1. And then over in A somewhere, it's going to add R0 and 2. So it's going to add these two numbers and store the result into R0 and set the condition registers. So if the answer is 0, then it will do this one. If R0 equals 0, it'll do this command. Otherwise, it'll jump to wherever this is. And if it's not equal to 0, it will add 2 to R0 instead. So here's the problem. When you got a pipeline, you got all these different stages, right? You got the fetch, and decode, and execute in a really simple 3-stage pipeline. In reality, the pipeline can have 11 stages, 12 stages. The barrel shifter is a stage, so on and so forth. And so we don't know until this value has been computed which way to go, right? And so there's something called a branch predictor. The branch predictor. And it's going to be like, I'm going to guess this one. And then it will actually fill the pipeline with commands, you know, there's add R1, you know, whatever. It'll start filling the pipeline with this branch. And then let's say that this finally finishes, it finally comes out of the pipeline, and you're wrong. Then all this speculatively executed stuff has to be, when it comes out of the pipeline, it's like, yep, sorry, you're dead. No, out. And then it has to, you know, do these instead. But if it guesses correctly, then there's no pipeline stall. And so the cost of an if statement is therefore complicated, right? Because it could be as little as 1 cycle, right? Because if it guesses correctly, then it goes to the right branch and it fills the pipeline with commands over there from the right branch. If it guesses wrongly, then it has to do a pipeline flush because the pipeline's been filled with commands from the wrong branch. And so, the cost of an if statement is either like one cycle or your pipeline depth, right? So if you have a pipeline depth of 10, then you have a cost of 10 if you guess wrong. And that's why, like when we were doing the earlier assignments, I was saying an if statement is 7 cycles, just to kind of give you an idea that they can actually be quite painful. Now, in reality, branch predictors are pretty good. So, especially on like modern, like an AMD Ryzen has AI branch prediction, and they can have accuracies of 90 something percent. A really simple branch predictor, like maybe on the Raspberry Pi, might not be nearly as good, right? And so they could get a branch prediction miss all the time, and then you have to pipeline flush. Okay. So does that make sense? What's going on, Nick Vicker? Yeah. So speculative execution means you speculatively execute one of the branches before you actually know if you're supposed to take it. And if you guess right, cool. If you guess wrong, all of those got to be poisoned and thrown out. Okay. Yes, SS does stand for the Secret Service, Tristan. I once went to a mystery murder theater in Vegas, which is pretty fun. It's pretty fun, and so the people running the place would give some of the people roles, like you're a musician or something like that, and so I just decided, they didn't give me one, so I just decided to be a Secret Service agent, and you're just eating dinner with these guys, and the guy next to me is like, I'm a light bulb salesman. I'm like, oh, that's a really cool role, dude. And he's like, no, I sell light bulbs. I'm like, oh, well, I'm a Secret Service agent. He's like, oh, that's really cool. Didn't question it. He just looked at me with like, oh, I've got my NSA T-shirt on right now, which always confuses people. Part of the EFF thing. Yeah. Now, apparently there's a lot of money in light bulbs. Like, I didn't know this, and I learned about it, and I apologize to the guy, for not thinking it was, I thought it was part of the theater, but it was not. Yeah, a lot of money in industrial lighting. Let's just put it that way. So, all right. Yeah, that's about it, I think. Superscalar, you guys understand superscalar. Multiple functional units. So if you have 3 ALUs on a 3-issue system in one cycle, if there's no dependencies, you could push out 3 adds at the same time. If you have 3 FPUs on a 3-issue system, you can push out 3 floating point commands at the same time. That way you could, in theory, have instructions per cycle of 3, right? If you have 3 functional units, you could, in theory, be doing, in triple issue, you could, in theory, be doing 3 instructions every cycle, assuming no dependencies. Indeed search, you do specs all the time? Yikes. Yikes. All right. Register naming is used when you have a loop and it creates a false dependency. The CPU can detect that and come up with a secret register. Register 45 that doesn't normally exist. This is more common on Intel systems because they have so few registers. And so Intel CPUs can detect false dependencies and rename them to boost performance. Okay, so yeah, all right. So let's talk a little bit more about memory maps and things like that. So when you launch your program, at program launch, it's going to have the minefield of doom down here around 0. The top of memory is at 7F, F, 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 F on a 32-bit system. Add a bunch more Fs for your grade on a 64-bit system. Wait, did I say that out loud? Sorry. You got your code segment down here. You got your BSS for all your globals here. You got your data segment here. You got your stack here. Okay. The stack grows downwards. Data segment grows upwards. Stack grows downwards with commands like push. Push is actually not a real assembly command. It generates an assembly command for you called stack decreasing multiple insert. I don't know. I don't ever use the actual assembly command because there's like 4 different kinds of stacks you can have, and just use push. So it goes downwards when you push things onto the stack, and it goes upwards when you pop things off. Pop goes up, push goes down. And how do you get more room in the data segment? Let's say you want a new memory. Well, there is a system command called break or sbreak that will increase the size of your segment, and it will give more memory to your program. So when you new something, new will probably call this system call, or maybe once, and it gets a big chunk of memory, and then new will allocate back variables out of it, and then when it runs out of room, it'll call break or sbreak again, get more memory from the operating system. And this is the lowest level version of your malloc or your new command. That's how they're implemented. They're using that system call there. Command sbreak, break or sbreak, part of the Unix standard library. Yeah, with sbreak you just say how much more memory do you want? I want 10 megs of memory. Just pass that in, and then it will send you a pointer to the start of the chunk of memory allocated. And there you go. And you can pass in negative memory too if you want to deallocate memory as well. Indeed, Searchlight Salesman. Int pointer underscore T. Yeah, all this is C, dude. So, int pointer type. I think. Yeah. You know, I don't call it that often, right? Because I call malloc if I'm in C, or you know, malloc is the C world version of new. New is C++, and I mean in C++, I don't really call new very often. I use vectors to manage my memory for me, or I use smart pointers. So, like for example, there is shared pointer, and there is unique pointer, and this is the C++ plus way of doing it. Right? Have we gone over shared pointers and unique pointers before? I kind of feel like it's important. Not really. I know I've mentioned it before, but they're actually really, really important. You guys want to learn some C++ real fast? I mean, it's, you know, we're leaping back and forth between the lowest, you know, memory management. Here's a chunk of memory, you know, do something with it. To like high level garbage collection, almost kind of stuff. Sure. All right. So we can do that on that in assignment later. Wouldn't mind it. Yeah, sure. Yeah, I'm actually probably going to show it in 41 tomorrow. For those of you that took 41 last year, you might want to actually watch the last lecture. I talked about some features of CSci in CSci 41 yesterday, enums and enum classes that maybe you guys didn't get last year, and they're doing the hash table benchmarking that I also think we skipped. All right, so delete M and E. All right. Vim Smarty Pants CC. All right. So they are in, was it the memory? Hashtag include memory. CPP. Shared putter, as Arthur Dwyer calls it. Shared putter. Yeah, it's in memory. Okay. All right, so so we got a class and foo, and it's got, I don't know, it's got 1,000 ints in it, and string. So this is going to allocate how much memory when we make it, when we new foo, right? So if we say foo pointer f equals new foo, how much memory does that allocate? How big is a foo? Big. 4,000 bytes. Yes, the array is 4,000 bytes. How big is the entire foo object? I've just new to foo. How big is that in bytes, if you had to guess? Depends on the string size. Yeah, that's kind of what I'm asking. How big do you think a string is? Things are empty, right? So when we knew it, the way C++ works is that it calls the constructor on anything that has a constructor. And if we built in a default constructor like that, that'll zero fill this array. And then these guys have, the string class has its own constructor. So when you call new, this is why new is better than break, right? It's typed for one thing. This plays very nicely with the type system. Whereas when you use malloc returns a pointer, just a void pointer. And you can get into a type conflict easily with it. So yeah, so when we call new foo, new is going to zero fill this array. So this array is going to be all initialized to zeros. If I did not have that there, it would not zero fill it. It'd be filled with random data. It will call the constructor on this one. It'll call the constructor on that one, which will initialize it to empty strings. So how big is this guy here? First name should be initialized in member initializer. Last name should be initialized. Sanitizer function. Unused variable. That's fine. 40, 48. Okay, so each one of the strings is 24 bytes, which nobody guessed, right? And so it's because even though it's an empty string, the string class itself has a pointer to the beginning. It's got a pointer to the end, and I think it's got some other member variables in there as well. And so it works out to 24 bytes just to hold an empty string like that. Let's see if that will make it not complain. Okay. Unused variable. I don't care. It's an unused variable. Okay, so I can say f points to first name equals okay, so this is all CSI 41 stuff, right? You make a pointer, new will allocate a chunk of memory, and it returns a pointer to the beginning of that chunk of memory. The chunk of memory is 4,048 bytes long. This will actually probably allocate new memory. It won't show up in here because this guy has a pointer, and that pointer is going to be pointing at something else. And we set the first and last name, we print it, and then we can read and write to the array inside of it, and then what did I forget to do? Oop, it does not like that. It's private. Thank you very much. A struct. Yes, indeed. All right. So, what did I forget to do? Did I violate the rule of Sith? Yeah, I did. Remember? Do you guys remember the rule of the Sith? There is one master and one apprentice. So, for every new, you need to delete. Exactly one new, exactly one delete, right? If you new this twice, you're going to leak memory, right? That's again, this is memory leak right here. Do you guys see that? You guys understand why this is a memory leak? Vacalar, do you see why this is a memory leak? Always two there are. One new, one delete. Right? And so if I were to do this, then I would need to delete F, right? In between, now we cleaned up the memory leak. Right. Let's say we don't do that. Do I have asan on here? I do not. Okay. So let's first of all, it's G++, Smarty Pants. Redeclare. Thank you very much. Yeah, it'll run fine. A memory leak will run fine. Right? If, however, we did a delete F. Let's see. That could very well crash. There we go. I newed it twice. I need to delete it twice. Nope. Nope. This leaked memory, and then that deleted this memory, and then that is a double free, double delete, and that will crash. Okay. So yeah, so that's why Java is top tier. Right. So let me tell you something. C++ can actually handle memory just as easily as Java, and better, because Java's garbage collection is non-deterministic. You don't know when it's going to run. There's ways of mitigating that, but if any of you guys have ever run a Minecraft server, I'm sure that if you care about performance, who here is a Minecraft person? Wheeler is. Yeah. Where is... Kearney just like that comment. Yeah, so have you guys ever messed around with the memory system on Java, trying to get like the Minecraft performance to work not terribly? Jacobson, you know what I'm talking about? Yeah, it's a pain. It's a real pain. And so Java exists because this is a pain in C++. Experience has showed us that programmers are just not smart enough to new and delete things properly, especially when it's in main like this. There are techniques that we use. We use the resource acquisition is initialization. We use RAII, Ray, sometimes called, where put news into constructors and deletes into destructors, and that helps a bit. Like with the string class allocates memory in its constructor, or it will allocate memory when you copy things into it, like down here. That'll allocate memory, and then the destructor cleans up after itself. So if you use the vector class, if you use the string class, it won't leak memory. It's actually very good. The constructor and destructors are a good way of bracketing the allocation and deallocation of memory, and it actually works fine. But when you're doing things like this, where you're just like newing things out in main, and maybe you're passing it to a function, and that function is responsible for destroying it, and the guy writing that doesn't know he's responsible for destroying, because all he's getting is a pointer. And if you pass a pointer to somebody, that doesn't tell you if you're supposed to destroy it when you're done with it or not. So what happens is experience has shown us that programmers are just really bad at actually newing and deleting memory. And so because of that, Java came along in 96 or something like that. And Java promised you don't have to delete things anymore. So the Java language would look like this, right? You can do things, you don't have to delete them. And the language itself will run garbage collection periodically. Garbage collection will determine which chunks of memory aren't accessible anymore, and then will deallocate them. And so garbage collection will periodically freeze your program. It traces through memory, see who has pointers to pointers to pointers to pointers, traces through memory, says, these two guys are not accessible anymore, deallocates them, and then it reruns your program. And that's fine. It's a very safe system, but it's kind of garbage. It's kind of garbage. So C++ has since then responded with a vengeance. To quote Good Will Hunting, there are better ways of doing memory stuff in C++ now. And so the biggest advancement in the past 100 years in C++ is the addition of -f sanitize equals address smarty.cc. And does not come asan runtime, does not come first in initial library list. Should do the link runtime to your application or load it. All right, you know what? I'm just going to move on to the regular server. I don't know if I've configured this properly. Actually, scp smartypants smarty.cc to wkearney at csci4x.com : boom. Yes, I will save you. Password is hunter123. And then let's just switch over there. I don't need to be on the Raspberry Pi right now. So I do now have asan. Look, it's the same server, but different. This is the old server you guys are used to. So look, it's on there now. Yay, secure copy. Neat. Secure containment protocol. All right, so if we g++ smarty.cc and run it, it's not going to complain because I don't have there we go. So with Address Sanitizer turned on, Address Sanitizer says, by the way, you have 2 memory leaks. You have 2 news, you don't have deletes on them. On line 13 of smarty.cc, you allocated 4,064 bytes. Why is it 4,064 bytes? On the other server, it was 4,048 bytes. What happened here? Why did it get bigger? Mystery. Why did it get bigger? That is correct, Rivera. Yeah, we moved to a 64-bit system, and so pointers went from 4 bytes to 8 bytes. Okay. So we could probably deduce from that how many pointers there are in a string class. Okay. So anyway, vim smarty.cc, and if we put one of the deletes back in, yeah, then it's even worse because we are now using it after it's been deleted, right? So if we put this here, we are now using something after it's been deleted. Address Sanitizer very rightly complains about that. Let's put it up here. And this is not complaining because I g++ instead of compiling it. There we go. Okay, so now I only have 1 memory leak, and so I need to put another delete like down here, and then everything's fine. All right, so I promised I'd tell you guys about smart pointers. So first big tool, though, is Address Sanitizer, right? And when you guys go to another institution, which I hope all of you will, this is not something the Jedi will teach you. Okay, so I have students at institutions all over, mostly California, and I'll actually say the same thing to you guys because it's getting close to the end of the semester. Wherever you guys go and you take classes in your junior and senior years, let me know what kinds of things are expected of you to know so that I can modify what I teach. Because I try to teach you guys like useful stuff that will prepare you for junior and senior years. And if I'm not, then I need to know that. So my spy network from around California. I'm Varys the Spider. Probably shouldn't pick that as a metaphor because he's a eunuch, but whatever. I'm a Unix wizard, so it's pretty close. Right? Varys was a eunuch. I'm a Unix guy, so pretty close. All right, so yeah, so something that equals address. This is something you need to take with you, by the way, because I have this set up for you guys, and not a single student I've had go to another institution has a professor that's told them about this. A lot of professors use Valgrind. Valgrind is a tool that will detect memory leaks. So let's put a memory leak back in. Let's put a memory leak back in. And so let's do G++, Smarty Pants, Valgrind a.out. So Valgrind will run it, and Valgrind says we lost 4,064 bytes. So Valgrind is how we used to detect memory leaks, and apparently at most institutions still is how they do it. I use Address Sanitizer because it will actually tell you what line of code it's on, right? So this one will. Let's try this. It will detect memory leaks, and Valgrind is actually a really useful tool, right? It's not. I'm not really talking smack about it, but the Address Sanitizer is just better. It detects leaks in real time. You will observe and report. Kearney Spy Network starts now. Okay, so that's this is the first thing. Take this with you. What? How does Zelda begin? You will. What is it? You will need this. It is dangerous to go alone. Take this. Yeah. That one. So whatever you see or CSU you guys go to, remember that. Okay, because that is the single biggest lifesaver. Trust me. Like at UC Santa Cruz, one of my former students was like, yeah, thank you. Was like they were having to do linked list in C, which is kind of a questionable thing, but whatever. And so one of the big things was memory leaks, and so they had to use Valgrind to detect memory leaks and things like that. And in my opinion, if you just always compiled your code with -f sanitize equals address, it'll just tell you immediately this line, that's where you allocated memory, you didn't deallocate it. It's really useful stuff. Okay, second big tool. So number one big tool, Address Sanitizer. Number two, smart pointers. Okay. So we have not done smart pointers yet, so we've hashtagged include memory. Okay, so how a smart pointer works. It's pretty similar to how Java works. In Java, you knew things, but you don't delete them. Okay, this is one thing you should write down or take a pic of, if nothing else today. Yeah, Zelda, definitely take a picture of Zelda. So smart pointers are there's two kinds that we use. There are shared pointers, can be copied. Unique pointer cannot be copied. That's the difference. So there can only be a single unique pointer. If you return it from a function, that's fine because it moves out of it. If you return it from a function, the original copy goes away, so it moves the pointer out. That's fine, but if you pass it to a function, you can't pass it to a function unless you move. You call std move to move it in general, unique pointers shouldn't get passed around too much. Like, don't use them for like linked lists and things like that, because shared pointers, I don't know. It just depends on what you need. If you need something, if there should be enforced a single copy of a pointer, then use a unique pointer. If you want to allow copies of it, use a shared pointer. There's not one that's really the default, although some students will sort of default to using shared pointers just because it gets their code to compile more often. So how do they work? So how they work is they shared. So rather than newing memory like that, you can say shared pointer to a foo named f, which is equal to make shared foo. Okay. This okay. Remember, pointer is just an int, right? And so when you new something, it just returns an integer, a 64-bit integer in this case, right? A shared pointer is actually an object. It's a part of the class. It does this thing here does the same thing as this thing here, but it does it more cleanly. So what happens is make shared allocates memory and returns a shared pointer to it. And so a shared pointer works the same way. In fact, you might notice that all of this code here compiles because shared pointers have a overload for the arrow operator. And so it actually is a drop-in replacement. Let's compile this. No match for operator equals. Oh, yeah, can't do that anymore. Right? And we can't delete it. You can't delete a shared pointer. But look, the code works. Right? No memory leaks. Right? So even though I deleted the delete, I used the delete to delete the delete. So check it out. Do you guys see this? That's all you need to learn. Syntax is the same for unique pointer, except it's unique pointer and make unique. Which in this case I probably should be doing because I'm not copying it at all. So unique pointer, make unique. Okay. And that's it. So it's very, very similar to new, except a shared pointer detects when there's nobody able to access that memory anymore. So when a unique pointer goes away, when it goes out of scope, when it hits a closed curly brace, it automatically deallocates its memory. You guys with me? So you no longer need to worry about the rule of the Sith. You don't have to make sure your news, your deletes are matched anymore. This gives you Java level memory safety, right? You can't leak memory. You can't. There's no deletes, so you can't double delete it, right? You can't mess up a delete if you can't delete it. You know what I mean? And you know, if you tried newing it twice, like if we said f is equal to make foo, again, is this gonna leak memory? We've just done 2 news in a row. Let's find out. Nope. What happened? Well, when we did a second make unique, the class is intelligent. It's like, oh, I'm trying to copy over some new memory. Let me delete the old memory first. And so if you stick to using shared pointers and unique pointers, you basically can't leak memory. There is a small caveat to that, which is if you use new with them and the new throws an exception, then I believe they can leak memory. But don't use new with them. Just do it this way, right? I don't even remember the syntax on new. Let's see. Shared pointer foo g. It's like new foo. Something like that. Yeah, so this is don't do it this way. You can. So shared pointers can actually wrap around a raw pointer. So if you pass it a raw pointer, in this case, a raw pointer is what new returns. It just returns a memory address. Those are called raw pointers. Remember, raw is war. You can pass a raw pointer to a shared pointer, and it will take ownership of it. But nah. Because if this throws, then it gets into a situation where like memory was allocated, but it throws, the object doesn't get called, the constructor doesn't get called, and so it doesn't know about the new memory, and so the memory is leaked. And so, no, don't do it. Don't do that. I'm showing it to you for completeness sakes, but don't. Use make unique or make shared. This is all you need to know. And if you do this, then what happens? Well, once that chunk of memory is no longer accessible, then you will automatically delete it. Question: if you have a linked list, you have a doubly linked list, and everybody's pointing at each other, how do you delete a node out of it? Right? You can actually, this is something that students try to do a lot, where they try deleting something by just saying like f equals null pointer or something like that, right? And so actually if you set the pointers to a chunk of memory, if you set both the pointers to it to null, then it's no longer accessible and the thing will get deallocated automatically. This is how a lot of students in 41 tried deleting a node from a linked list. They tried just setting the pointer to it to null. With a shared pointer, it'll actually delete it. So, but you have to make sure both of them get set to null. In general, it's a little bit dicey using shared pointers with a linked list, because what if you have a circular linked list and everyone's pointing to each other, and if the whole list can't be accessed, then it'll still not deallocate because everybody's pointing at each other. It's like everyone's holding hands. I'm not gonna let you go. I'm not gonna let you go. And so there's something called weak pointers, which I don't really want to get into, but in general, if I was building a data structure, I would still probably use new and delete with raw pointers. Because in a data structure you can control, you can do the array, right? In data structures, if you're making a binary search tree, I would just probably use a raw pointer. Like that. Yeah. There's a little bit of an overhead to using a shared pointer. It's got a counter. It's got what's called a reference counter, so it counts how many people are pointing at it. And when it hits 0, then it deallocates. So there's a little bit, and it's a little bit slower, and it's a little, it's like I'm good enough that I can write a binary search tree without leaking memory. But if I'm ever going to be doing news and deletes in like main or something like that, because there are tricks that you can do with pointers that you can't do with a regular variable. But then that exposes you to the risk of leaking memory. And so in those cases, I would, and pretty much very close to 100% of the time, I'd prefer using a shared pointer or a unique pointer rather than a raw pointer. Because if it's a raw pointer, you could forget to delete it. For example, in CSI 41 right now, there is a raw pointer in main to do tricks with inheritance, and some people are leaking memory because they probably, I don't know what happened, but if you forget the delete, then 2001, 3 billion devices run Java. 2018, 3 billion devices run Java. Yeah, sounds about right. Probably less now, because they have been deprecating Java for a long time. Like let's see, what was his name? Carl Weinman, Colorado, FET, I think. Carl Weinman, yeah, Nobel laureate. He worked with a person who's in grad school with me, Beth Simon, who's at UCSD as a computer science professor now. She's a very, very smart person. She worked on this as well. So this website here is a bunch of interactive simulations for physics and things like that. And so it used to have a lot of balance. There we go. And so I don't know. Let's put some stuff out here. Boom, and boom. Run. There you go. And so you can learn about leverage and things like that from interactive physics simulation. So if you guys are in physics, PhET is a really cool website. I don't know if you guys have seen it before, but it's super cool, super neat. And it used to have, why am I mentioning it? Because it used to have a bunch of Java applets on it. And as you can see now, everything is HTML5 now, right? Because they've been deprecating Java for a long time. Java was supposed to be this secure way of running programs over the internet. Like nowadays, Java is mostly used as a desktop runtime, right? So you can run a Java application on a Mac or on a Windows machine or on a Linux box, and it runs the same on every system, in theory. And but originally, it was designed to run over the web because there was a company called Sun Microsystems, founded by, you don't know, Sun Microsystems. It's called Torx, or you don't know, Sun Microsystems. Anyone heard of Sun before? They were originally sort of the dominant Unix vendor out there, and I had friends that worked for Sun, and they had some really cool technology. Like they had hot swappable everything. So if you had a Sun server, like the early internet was basically run on DEC alphas and Sun machines. Linux has sort of eaten everybody since then, but they created Java because they were worried that they would go out of business. They created Java because Windows was destroying them in the desktop side of things. Their desktop boxes were like $5,000, so businesses would buy Sun machines, but there was way more volume in the PC market. So what they had the idea was, like, if we create a new programming language, they could run equally well on every platform. Then people will just start making programs in Java, and then Sun will have programs finally. Like maybe somebody will make like an open office in Java, and we can actually have an office suite on Sun. And then they went out of business. So yeah, but they had really cool stuff. Hot swappable everything. You could have a server running, and you could pull like the CPU off and put a new CPU on, and it would keep running. Like uptime, like 99.99999 uptime was like their goal. Like rebooting, what? No, you don't have to reboot your system. You know, like slap some more RAM into it. Who cares? You know, you don't have to reboot. Anyhow, I was asking who founded it. Bill Joy. Do you guys know what Bill Joy made? Vim, or VI. The original. Vim is a version of VI. So, the dude who made the world's best text editor also started one of the world's most influential tech companies. So, yeah, Bill Joy is, yeah, you know, he's done two great things in his life: VI and Sun. He's done other stuff as well, actually. Come to think of it. So, yeah, all right. So Java was made to be a safe, secure thing. And the notion was you could actually run programs over the internet. Like somebody would send you a program and it would run inside of your browser. And they couldn't get it to work. I mean, it worked, but to get it to work securely, they couldn't. And so if you check out PhET now, all those Java applets are gone. You know, it's a real shame, too, because like I think Firefox and Chrome will just refuse to run Java applets. So there's a big chunk of the web that just doesn't work anymore because the browser's just like, we're not going to support it anymore. It's not secure. It's kind of annoying to me. Because there's a lot of, you know, there's a lot of stuff with no replacements, you know. So, but that was like really the main purpose of Java was you could write a program that would run in a browser, and JavaScript has taken over that. JavaScript is no relation to Java. They just picked the name for the branding purposes. yeah, so client-side JavaScript is what browsers run now. Before, it was JavaScript also, but there's a lot of Java applets that would download the program to you and run it in your browser. Java is JavaScript, what ham is to hamburger, what car is to carpet. Yeah, Flash, same reason, right? Flash has been deprecated. FET used to have Flash applets on it as well, and those are all gone. Okay, so C++ countered Java with this, right? And so with this, actually this will probably crash, won't it? Let's try that out. Yeah, because we're setting it to null, and then we're using it, right? So, if you do this, though, it'll deallocate the memory. Yeah, and so basically, with a shared pointer, you just knew the memory. It's just like Java. You knew the memory and then never delete it, and then the system will detect when that memory is no longer accessible and free it for you. And so you have the speed of C++ and the memory safety of Java. So, best of both worlds. Best of both worlds is C++. Now, does C++ enforce you using these tools? No. And so there's a lot of C++ code out there that is still memory unsafe, that leaks memory, that double deallocates, and all this stuff. But hopefully, as time goes on, and if you were to like start a company and doing coding, you can enforce these rules, right? All development must be done with address sanitizer turned on, and that's sanitize equals undefined. And turn on undefined behavior sanitizer. So if your program does any undefined behavior in runtime, it'll print an error message to you, or a warning, one or the other. So you can, like at the company level, you can enforce these rules. All development must be done with address sanitizer turned on. Always use smart pointers unless there's a good reason not to. Sometimes you do want just a raw pointer to something. You just want a pointer, and you pass it to something. As long as you're not expecting them to delete it or anything like that, it's fine, I guess. But in general, just mandating smart pointers is the way to go. Do people in Frankfurt eat frankfurters? Hamburg steak is really good, by the way. Have you guys ever had Hamburg steak? That. It's like a steak that's kind of like breaded and baked and has like this gravy on top of it. Man. Japanese people love it, by the way. I've had Hamburg steak more times in Japan than I have in America. There's actually a restaurant in Ueno Station that I hope it's still there. It's coronavirus. Yeah. Okay. Yeah, it's really, really delicious. Okay. Any questions about smart pointers? Because that is a new C++ thing. Do you guys want to see some of the tricks that I showed the 41 people yesterday? Are you guys learning C++? Okay. So, okay, so how many people here have seen enums before? I teach them occasionally. Muya, it doesn't count. You were in class yesterday. Used in game design. Yeah, I don't know what they do, though. Yeah. So what this does is when you make an enum, it just makes a bunch of constant integers that have different variables, or different values. So this is very commonly used on like a menu. It's like if you're making a menu of options, people will oftentimes use an enum. because that guarantees this is option 0, option 1, option 2, option 3, option 4. And if you were to add a new option, just it makes sure that everybody gets their own unique number. And you honestly don't really care what the number is. Like, we don't really care that change settings is option 13 or 14. Like, it doesn't matter. All that matters is it has a different value from all the other ones, right? So you can say when they select something, if the choice was constant, you know. And so by doing enum mode linear chaining like that, that is equivalent to writing constant linear equals 0, constant chaining equals 1. So these two lines of code, and you can see it's actually complaining at me because it has done it already, right? It has done it already. So can't redefine linear and chaining. They have been made for you. And if you want them to have a different starting value for whatever reason, you can start them at 10. Then chaining would be at 11. But it's fairly uncommon to do that. It's not super uncommon. It's a little uncommon. Because usually you don't care what the values are. Like, you don't care that linear is actually 0. All that you care is that linear and chaining have different values. So that you can say, like, if choice equals linear, then do something. If choice equals chaining, do something. They also play really nicely with switch statements. You know, the switch statements are things that I kind of hate because of all the different bugs I've had to track down in students over the years. Switch statements are actually really nice with enums, because if you switch on an enum, the compiler will actually say, hey, you know, you have cases for these 4 parts of the enum, but you forgot one of them. And so the compiler will actually warn you if you add something, like, let's do double hashing or something. If you add something to the enum and you don't add it to the switch statement down below, then it'll be like, hey, you forgot something. Like, oh, cool. Hey. So enums and switches go really nicely together. All right, makes sense. Pretty easy, pretty straightforward. It's just an int, so int mode equals linear. Alan, does this make sense to you? Pretty easy, pretty straightforward. Then there's enums and there's enum classes. And so the enum class has the, do you see the syntax difference? That keyword right there, it went from being an enum to an enum class. And an enum class does, in general, the same thing. It makes a bunch of constants. But they're not ints. You can set what the underlying type is. In this case, I'm setting the underlying type to be char to save memory, because I don't need an int. You know, 30, waste memory, right? You can set what the underlying type is. A lot of times you don't care about that. Here, though, I care about it because I'm making a vector of them. I'm making like 1 million of them. So, yeah, I want to shave memory down. But these things are not technically ints. They will not cast to and from an int. Like you saw in the previous thing here, these are just ints. And so you could say int mode equals linear. If mode is less than linear or mode is greater than chaining, mode equals linear. They're just ints, right? With with a enum class, these things are just their own values, okay? And so if you have enum class status, then you access them by saying status : open. Do you guys remember what : does? Do you know what the : operator is called? I can't believe I'm drinking black coffee and enjoying it. That's weird. I normally need some cream in my coffee. It's Colombian coffee. From Panera. It's their newest kind of coffee. So, not bad. Not bad. Like, normally when I drink black coffee, I'm like, for real, I didn't know Panera had decent coffee. This is new apparently. So, yeah, they got like a pretty good Colombian brew. Even drinkable black, which is weird. Scope, yeah. See, Mui is giving the answers from class yesterday. So the double colon is called the scope resolution operator. And so if you ever done std std : something, std vector, you know. The colon means the thing inside of the other thing, right? So the vector class in the std namespace in this case. Here, when you say status : open, that means the value of open inside of the status class. Have you guys ever made a class function outside of the class? Like if you had a class function called, I don't know, get size or something, it would look like this. Size t hash : get size or something like that. You guys remember that? Like when you're writing functions outside of the class, use the : to indicate I'm writing the get size function of the hash class. Right? Okay, so with an enum class, this is a lot more strict than enums. I actually use enums more often because having them be integers is just a really nice property. You can just write a for loop and count upwards and stuff like that, and do each of the enums. With enum class, these are just 3 values. This is a type. It creates a type called status, and you can make a vector of statuses, and each one of the values in that vector can be either status : open, status : filled, or status : deleted. It is very strictly typed. They're not ints. And so this says set all the values in it to be status : open, and then you can check to see if the status at a spot is filled or not. If it's not, then we write the data in and we set the status to be filled. Okay, you guys understand? And you can't. This is not an integer anymore. If it was an enum, you could be like 1, right? And that would be the same thing as this, because that would be 0, that'd be 1, that'd be 2. This won't compile because it's not an integer. It's just its own thing. There's 3 possible values: open, filled, deleted. That's it. Okay. So it's like you've created a type that has 3 values in it. So rather than an integer that has millions of possible values, there's 3 possible values. So you make sure it is one of those 3. Okay. Make sense to you guys? Wabe, does this make sense to you? What error would it throw? Let's find out. The preprocessor is not, or the COC is not complaining about it. Yeah. Cannot convert from integer to status. Yep. It is not an int. You can't, even though behind the scenes it's going to have the value of 1, it is very strict about it. It's like, no, I'm not an int. You can't accidentally set it to like a number. No. Not convertible. All right, so anyone else have questions about this thing? It's pretty common for people to use enums. Enum class does not supersede enum because sometimes you do actually want them to be integers, right? If you want to do a loop starting at the first element in the enum, going to the last element of the enum, you can do that. You can't do it with this enum class. You can't do a range-based for loop for every element in the enum. Nope. There's proposals right now before the standards committee to make better enums where you can do something like that, where you can say like, for each option in status, do something. Nope, not right now. Just there's 3 values. That's it. Cavett, Jeff, any questions about this? I had to make them determine which shells are walkable, flyable, and swimmable. Yeah, that's pretty common use. Sure. But you just have to choose whether or not to use an enum or an enum class. And sometimes one of them leaps out as being the better option. Are you guys still here? You guys are getting advanced C++ stuff right now. All right, let me show you one more thing we can do with pointers here. Main.cc. And so this is a pointer to a hash table. What is a pointer? Just an int, right? So what is this hash class that I've made? What is this hash class that I've made? Well, this is something called a pure virtual or a pure abstract or an abstract class. So this is a class that has absolutely nothing in it. Okay. In Java, this would be called an interface. So an interface in Java would be something like comparable. Comparable means that if your class implements the comparable interface, it has a less than operator defined. It's not they don't have less than operators, but that's the general idea. And so what you can do is you can say, in Java, you can say, this data structure I'm making can only hold comparables. And so only things that implement the comparable interface can be stuffed into this binary tree, right? Because in order to do a binary tree, you have to have a less than operator, right? And so this is the C++ equivalent of this. This is a class. You can't make a variable of hash type, right? Because all of these things equals 0 means the function does not exist. Okay? So you can't actually make an object of type hash. If you try hash Bob, then it will say no constructor. Yeah. Sometimes it'll say trying to instantiate a pure virtual or trying to instantiate an abstract class. You can't do it. Can't do it. So, yeah. So what's the point? What's the point of having a destructor? So this is a weird mal feature of C++. You need to have a virtual destructor because the virtual destructor will allow the destructor on the subclasses to be called. If you don't have this, it will call the destructor on the base class, which doesn't exist, and it won't free up the memory in the subclasses. So basically, anytime you do something like this, you need to just make an empty destructor that's virtual, and then it will successfully call the destructors on the Git classes. And if you don't do it, if you don't do this, I believe it'll warn. Yeah, deleting object of abstract class type hash, which has a non-virtual destructor, will cause undefined behavior. Yeah, it'll warn you if you don't do it. So. Okay, so what can you do with a virtual class like this? Well, you can subclass it. And so what I have here for my CSI 41 students this semester is they have to implement 2 different hash tables. And you guys are going to have to implement hash tables in assembly. Yeah, that's the next assignment. I've been promising it for a while, and that's coming up. Okay, in fact, I might even give you this assignment. And then have you write the functions in assembly. That could be fun. A pure virtual function is a function that you make virtual and set it to 0. Yeah, and so this function doesn't exist. You can't call it. And but what it does is it makes an interface. So it says anybody who subclasses off me, anybody who subclasses, there you go, public hash, anybody who subclasses off me must implement these 4 functions. And so you know that anybody who subclasses off of hash is going to have an insert, a remove, a search, and a change. Okay. And so we've got two different subclasses of hash. We've got linear probing, and we've got chaining. Okay. And both of these implement that interface. So you see that chaining has an insert, remove, a search, and a change. And linear probing has a insert, remove, a search, and a change. They implement that interface. Is that why you don't need to type override on the other functions besides the subclasses? You can put the override keyword here if you'd like. It doesn't do anything. Override is a hint to the compiler that you are overriding a virtual function. And so it's useful if somebody forgets to make the parent virtual, you know. It doesn't really do anything. Probably good practice to do it that way. Anytime you have anytime you're overriding a virtual function, it's probably a good idea to call it that. Cannot convert. Unused parameters. Jeez. Let's turn off those warnings. Do you guys know how to turn off warnings, by the way? So I like turning all the warnings on. There's only two warnings that I kind of don't care about too much when I'm doing development. That's unused parameters and unused variables. And the reason why I don't care about when I'm developing them is because I'll stub out a bunch of functions. And it sits there like, you haven't done this one yet. I'm like, I know. I'm getting to it. And so I'll turn them off. But at the same time, when you're done, you want to turn them back on to make sure that you didn't forget any variables that you're supposed to be using, any parameters you're supposed to be using. But if you want, you can turn them off by, anyone know? W everything. Right, so there's all warnings, but that's not all warnings. So there's extra warnings on top of all warnings, but that's not all warnings. There's pedantic warnings, turning pedantic warnings into pedantic errors so that it doesn't compile. And then there's -w everything, which is, I think, only in Clang. I don't think G++ supports that. It doesn't know about everything. So do you know how to turn off a warning? There's a couple different ways of doing this. So this warning is called unused parameter, right? And turn them off by fixing the mistake. That's one way. Yeah, but like when you're doing development, it's very useful to like have warnings for all those stub functions. It's like not there. And so you can do a pragma, which I'll show in a second. But here's the error message, right? Warning unused parameter. So if you want to turn it off, you say no unused parameter. There might be a hyphen in there. So make clean. No unused parameter. There you go. And so you slap a no in front of it. Whatever, like whenever it warns, it tells you this is warning from unused parameter. So if you normally have -w unused parameter turned on, it turns on that warning. If you slap a no hyphen in front of it, it turns off that warning. Okay. And the other way that you can turn off a warning is with pragma. But you have to do that in front of every one, so it's kind of annoying. I don't really do it. But pragma, is it no unused warning, something like that. You could look it up how to do it. And then it'll turn off the warnings on that function. And then as you implement, you can pull those out. So it's more fine-grained control. Like you can turn them on and off on each function, right? Isn't it -w? Dash lowercase w, right. But, yeah, I don't know. It works. All right, so then, yeah, let's come back into here and talk about this. And then for the last half hour, we'll go back to talking about memory issues, architecture. So what we have here is a pointer. Right? We have a pointer to a hash table. And the way that inheritance works, and now that you've taken assembly, like how inheritance works actually will make a lot more sense to you. Okay. So this is a pointer to any sort of hash table. Anybody who implements the hash interface, it can hold. This won't work with a regular variable. It has to be a pointer. Has to be pointer. If you try doing that, it won't work. It's an abstract class. You can't actually make a variable of type hash. But you can have a pointer to a hash. If you have a pointer to a hash, that means it'll point to anybody who implements that interface. Like I said, pointers are actually useful. Beyond like the newing and deleting things, they're actually useful. And that's why we do things like make shared and make unique. Because they're actually useful. You can do tricks like this. And so what we have here is a pointer to any type of hash table. And then depending on what the user typed in, is it linear mode or chaining mode, then it will either new linear probing hash. The result of that pointer is a subclass of hash. So the pointer to hash will accept a linear probing hash. And so when you call change on it, it will call the linear probing hashes chain. Whereas if you set it equal to a chaining hash, it will call the chaining hashes change. So you can switch out which functions are being called. You guys see that? So with just these 2 lines of code here, I can switch out the implementation on the hash table. So the hash table can either be doing linear probing or it can be doing chaining. And just with those 2 lines, I don't have to copy and paste all my code. I don't have to make 2 different variables. None of that stuff. I have a pointer to the base class, which is hash. And then just based on which option they pick, it'll switch in a different implementation for it. Pretty cool stuff, right? At least I think it's cool. You guys see that? So linear probing hash and chaining hash are both subclasses of hash. Hash is a pure virtual or an abstract class. There's like dead silence in Discord right now. But this is why we do that, right? So you have an interface, and if anybody implements an interface, then they can become the next Dread Pirate Roberts. Right? They can take over they can be table. This is a common object-oriented trick. Object-oriented tricks. Just Muya. Nobody else has anything to say about this? I think it's cool, dude. At Kearney. So, what should I do next? How should I make this even better? Add flames. That's a good idea. What did we talk about earlier in the lecture today? Cherry pointers, yeah. In this case, not a cherry pointer, unique pointer. So we can up here, actually include memory, and we can say unique pointer of type hash. Like that. And then we can say equals make unique. See if that works. I hate it when it inserts parentheses for you. It tends to break everything. Let's see here. Assigning to unique pointer from incompatible type. Make unique object. What do we got here? Yeah, better. I'll figure it out later. But that's the general idea. Schemad, you good? All right. Yeah, but that's the general idea. The trouble with what we have right now is that we have to remember to delete it at the end, right? And if you use a unique pointer, then you can you don't need to worry about the delete. Okay. Very specific type of pointers. Don't forget your F sanitize. What was the command to copy and paste the whole line instead of highlighting it? YY. YY copies the whole line. YY P pastes. If you're doing it using this, you're wasting your youth. Do you need this star on the table? Probably. Yeah. I'm probably doing something stupid. I haven't had enough coffee today, so I'll look at it offline. Okay. Let's see, did I break anything? Good. All right. So that is that. Let's talk about more memory stuff. So we're talking memory stuff. We just did smart pointers and stuff like that, so you can have Java style freedom to be a bad programmer. Now, last time we also talked about where the operating system lives, and so the operating system, depending on your perspective, either lives down here in nega space, or it lives up top in the cloud kingdom. One or the other. Okay. Is the OS lives, FF. And so the operating system has chunks of memory that are dedicated to your Ethernet card, your Wi-Fi, your graphics card. And you normally can't access any of this. All of this is off limits to you. In order to request access to the OS's memory, you have to call Nmap. Nmap will take a chunk of the memory and it will stick it into your address space somewhere. It'll return a pointer saying, here's the spot we found for you. And then you're able to read and write to this spot, and this is actually going to be the graphics card. So if you Nmap in the graphics card, you can read and write to it directly. And you can program the graphics card directly without any overhead. It's pretty cool. Yeah, so Nmap, very neat stuff, and allows you to, you can share memory with other programs. You can open a file as if it was, and you can just have like a chunk of your memory be a file, and you can just read and write to it like it's an array. It's pretty cool stuff. It's very fast. Pointer to a unique pointer. Yeah, I don't know. I'll play with it. Okay. So, any questions about Nmap? The code for it. Is a different one from what I showed last time, but this probably wasn't recorded last time either, so I'll just show this one so everybody gets new stuff. So this is going to copy from one file to another. It's like DD, basically, if you're familiar with that command. So this is going to open, this is a system call. Open file 1, read-only mode. Open file 2, read-write mode. Create the file if it doesn't exist. Truncate it to size 0. Even if it exists already, it'll be set to size 0. Permissions. Set to read, write, execute. Looks like the umask will override that. And then if it returns a negative number, it's an error. I don't like this formatting. It's a weird formatting. Let's see. A style. It's slightly better, I guess. So I don't like this. Okay. Have a hanging brace like a smart person. Okay. So stat, fstat is the C library interface to stat. Basically does the same thing. Stat, again, reports information on a file. How big it is, its permissions, that kind of stuff. Last read, last modified. This will jump to the end of the second file. And it's going to write a byte there. That will create a file with a hole in it. That's what we talked about last time, right? And then this is going to mmap the input file, mmap the output file. So that I believe means find any address you want to map it into, read mode, shared memory, file descriptor in is the file that's going to get mapped, no offset. And then for this one, it does the same, except it'll allow writing to it as well. And then it just calls memcopy. So memcopy copies from one array to another. So memcopy, you pass in a pointer, another pointer, because pointers are arrays are pointers. You pass in 2 pointers, destination, source, and how many bytes to copy, and it will just copy from one to the other. And it's up to you to do bounds checking. In C, you will hear that a lot. It's up to you to do the bounds checking. Don't, make sure that there's enough room in the place you're copying to, or you're just going to trample memory. So memcopy is a C library function, very commonly used even today in C++. Why not? There's also B0, which will zero a chunk of memory. There's minset, which will set, you pass in a pointer and a you pass in a byte, really? Byte, or is it an int? I guess it's a byte. So it fills the memory with whatever number you pass in there. So if you put the number 10 there, then it will fill the array with 10s. Okay. And so these are all part of the C interface for working with memory. Malloc, as we've talked about before, you just pass in a number of bytes you want to new, and it returns a pointer to the start of that chunk of memory. Free takes that pointer to the chunk of memory and deallocates it. So a very common task, maybe semi-common task at the junior level is to write malloc. It's a job interview question. How would you write malloc? So according to Zach DeFuria, that was the hardest assignment he got at UC Irvine, was writing malloc. And yeah, I never had to do it myself. So don't ask me. Malloc is the company that makes Frosted Flakes, I think, and things like that. Kellogg's Frosted Flakes. So Malloc will clear the memory. Realloc will increase the size of the memory that you have. I don't know what realloc array is. Let me see. Change the size of the memory block. Point to be large enough for a number. Okay, so it's the same thing as realloc. Okay. So, yeah, and so and so the way that it copies from one file to another is that they're just basically arrays. So it just reads from one array, writes to another array, but what it's really doing is it's copying all the bytes in the file over. And because accessing a file through Nmap, like I said, when I did a bunch of benchmarks, it was the fastest way of reading and writing to a file. So this is, anytime a computer science major hears fastest way to do something, you should perk up. Hash tables. Huh? Order 1. What? Pay attention to that one. Linked lists, don't care. Binary search trees, yeah, they're cool. Hash tables, sing. Nmap, it's good stuff. Okay. So one more Nmap thing here. So this is using IO stream for some reason. Is this C? Oh, it's C. Why is it using IF stream? The hell? Who wrote this? So okay, so this, again, system call, open the file. Read write, create the file if it doesn't exist, set the file to 0 if it does exist. These permissions, the user has access to read and write but not execute. The group and others have no permissions on it. Seek to the end of the file. The file size is set where? It's just a constant. Okay. So it's going to jump to the end of the file. Do some error handling. We write a byte to the end of the file to make it that size so that you can treat it as an array of that size. All right, so we memory map that file. Again, that file descriptor gets memory mapped, so this is a pointer to the array. The array is the file. You can write values to it. And then it's going to just write into the file multiples of 2, 2, 4, 6, 8, yeah, kind of stuff. And then if you want to unmap it, you just call memory unmap, passing in the pointer and the size, close the file descriptor, and you're done. So do you guys see how that works? Like that's, you know, there's code to set it up and code to finish it, the mmap and the unmap. But do you guys see, this is actually reading and writing to a file. Do you guys get that? And it reads and writes to a file very, very quickly. Probably twice as fast as the other alternatives. That's a file. So it's going to dump the multiples of 2 into it. The first element is going to be FFFFFFFF. Element 100 is, well, it's probably going to be overridden here. But the first element's going to be 2 billion-ish. Numents. Should probably be numents. Last element. To the end. Okay. Any questions? Turn a file into an array. And if we had Raspberry Pis, you can also use memory map to access the GPIO pins and turn them on and off. We don't. Here's the whole code. I don't know why there's. I think I was just messing around with this. So here's how you memory map a file. And if you're forgetting those things, like I did in an earlier lecture, like that's why you shouldn't do it cold from scratch, especially when it's not code you write very often. You know, if you forget one of these things, it won't work. So this will turn a file descriptor into a array. And you just read and write to the array, and then that turns it off. Can you go over the arguments for Nmap? Yeah. This is, I believe that's the memory address you're requesting that it allocate the memory at. If you pass in null, then it just picks a spot in your address space that's open. So usually you use O. That's how many bytes of the file you want to map. So for example, the file size is 4,000 bytes, then you map 4,000 bytes. It needs to know how big a chunk of RAM to allocate at this spot. Or if you pass a null, then it will pick a spot for you. This says, can you read or can you write to that file? So you remember how Hazelton and I talked about how the MMU can map in pages, memory pages, as read-only, or write-only, or execute bit. And so that's how you set the permissions on it. So I'm saying I can read and write to this chunk of memory. If you're just reading from it, like in that other example, you just use prompt read. And do you guys understand the vertical slash? We've talked about bitwise or like in 41 and in this class, I think, and maybe in 26. So this is setting two different options. These are powers of 2. And so that might be, I don't know, 8, that might be 32, I don't know. And by bitwise ORing them together, then you can set multiple options in one argument. So it's a very C thing to do, to pass in 5 different flags, bitwise ORing them all together. Map shared means shared memory. I don't recall what the other options are there. That's the file. Remember, a file descriptor is just an int. So when you call open, it just gives you an int. This is file 7. You open a socket, this is file 8. You open a pipe, this is file 9. All those things you read and write to are just ints. And so in this case, you're like, take file 5 and memory map it. And this is the offset. So this means starting at the beginning of the file. If I passed in 2000, it would start halfway through the file or whatever. You know? So, yeah, in general, that's going to be 0. That's going to be just the size of the file. That's the file descriptor. It's probably always going to be 0. Read and write is pretty standard, and then map shared is standard. And so that will turn this file descriptor into an array. Map is an array. It is a array of integers. That's it. And then whatever you read and write to that array, it gets reddited. It gets read from and written to. Okay. And if you ever worry about memorizing that stuff, remember the man page is there for you. Man Nmap, and it will explain what each of these parameters means, right? If address is null, then the kernel chooses the address of which to create the mapping. This is the most portable method of creating a mapping. Yeah. If the address is not null, then the kernel takes it as a hint, but it'll pick the nearest page boundary. Right. So we talked about pages, right? Memory pages. Briefly last time. So a page is a block of RAM, right? Or it doesn't actually have to be in RAM, but you can think of it as a block of RAM. Okay. And what happens is, do we have any pictures in here? Smallest page size 4K, larger page sizes 4 megs, gig, 2 megs. Yeah, in general, they're going to be like a K, 4K, something like that. And I got page table. And so this is, remember how I showed you guys this last time? You've got your code segment, your data segment, your stack, and this one has the things going in different directions. It doesn't really matter, because as it turns out, the NMU will map them to actual physical memory. So every 4K of your code segment will be a different 4K of physical RAM. And it will try to keep them contiguous so that you get good caching, but it doesn't have to be. If you run out of room, then the next chunk of the code segment might be down here, for example. Okay. And so the MMU does this mapping for you, and every time you try accessing a page of memory, it checks to see, do you have access to it? If you try accessing somebody belonging to somebody else, it'll segfault, right? If you try going outside of your segment, it'll segfault. You can't actually know who is next to you in RAM, because all you see is the virtual space, right? All you ever see is the virtual space. I have complete access to RAM. Oh, they have, this is upside down. Okay. So this is 0 and this is 7FFF down here. Yes, it's upside down for some reason. So yeah, you have access to all of RAM, but what's actually happening is that the MMU translates each of these pages into a chunk of RAM. And then when you run out of RAM, which doesn't happen very often these days, but I guess still could, RAM's just so cheap that you just buy more these days. It used to be very expensive, $1,000 a K. $1,000 a K. It's a lot of money, and that's 1970s, 1980s dollars, right? There have been huge advancements in the speed and the density of RAM that have made all of our wasteful Call of Duty excesses possible. Back in the day, though, like, use a short name. You get 8 letters for your last name. Sorry if you have a longer name than 8 letters. You get 8 letters. All usernames on Unix had to be 8 letters, or passwords were like 8 letters. Like, you couldn't even have a long password. 8 letters, that's it. That's all you get. You know, Affavong, yeah. $1 a byte, yeah. So, like, it used to matter a lot more. Nowadays, you know, like, how much is RAM these days? It's like, I think the price of RAM is actually going up these days, right? Components, memory, desktop memory, 16 gigs for $90. Yeah, like whatever, you know. Whatever. So 16 billion bytes of RAM for $90, you know, it's enough. It's enough RAM to hold the social security number of everybody in China 4 times. You know, just on your desktop machine. You know, just on your desktop machine, whatever. I have 32 gigs on my desktop machine because it's like, all right, whatever. Spend another $90. I don't care. I don't think I've ever come close to running out of RAM on my current machine. All right, anyway. So anyway, so what happens though when you run out of RAM is that it will write these pages to disk. So you have something called a backing store or a swap file, and the swap file will take pages from RAM, and when you try accessing those pages, you'll get a page fault. And like I showed you last time, but didn't make it into the video because I was on a cell phone connection. Time man Nmap. So whenever you finish a program, it'll tell you how many page faults you have, things like that. And yeah, and then you've also got something called the translation look-aside buffer that caches these things. If you're jumping around in memory a lot, you can feasibly run out of room in your translation look-aside buffer. Start getting cache misses every time you access RAM. It's really bad. Yeah, that's another form of caching. Like I said, probably in CSI 41, there's 2 types of optimizations that are the most common. Caching and hashing. Caching and hashing. So caching, store the most recently used work. Hashing, throw RAM at a problem, jump to the right spot, solve it. Those are the 2 most common optimizations at kind of a big picture level. And so you'll find caches everywhere. So this whole thing here is cached. What's called the TLB, the translation look-aside buffer. Okay. So yeah, there's the TLB, and if you get a TLB hit, it's basically invisible to you. It doesn't slow you down at all, usually. So yeah, and the MMU also is the guardian of the galaxy. It prevents you from accessing the OS's RAM. It prevents you from accessing other people's RAM. You'll get a seg fault if you try doing that. Okay, so that is memory. That is the memory subsystem on basically all major operating systems. I'm most familiar with Linux, so if you have questions about the details of how Windows works, I can't tell you. I can tell you that Windows calls page faults hard faults for some reason. So if you go into the resource monitor and look at memory, hard faults right there. So that's how many page faults you're getting. So if you're getting page faults, then your system's going to start slowing down because you're using your hard drive for RAM or your SSD for RAM, and that's slow. So you can sit there and look at what everyone's doing. You'll learn more about what these different categories mean in your architecture class later on. But man, look at those cores working. Look at that. Got 16 cores all operating. It's a beautiful site. I mean, 3.3 gigahertz, 10 megs of L2 cache per core, 13 megs of L3 cache. Beautiful site. Beautiful site. What is it doing anyway? OBS, CPU, who's eating it? Discord. Oh, my backup's running. Okay, that's why. OBS is only 2% of my CPU. Not bad, not bad. Firefox eating up a gig of RAM. Discord half a gig. Steam 200 megs. Yep. And so these are all the kinds of things that when you go out into the real world and you're writing real world apps, you pay attention to them. You pay attention to your cache hit rate. You pay attention to your page faults. And if everything's going fine, then yeah, just kind of ignore them, I guess. But if you're in a performance critical environment, then they'll actually make that part of the regression testing. So if you put out a patch and your patch causes the cache hit rate to go up, they'll reject your patch, right? So all these concepts you're learning here, even though it's all like, oh, we're learning about the low-level operating system stuff. Yeah, you submit a patch and your boss doesn't accept it because you caused more cache hits. Yeah, but it looks cleaner now. I don't care if it's cleaner. The cache hit rate went up significantly. Redo it, right? So you got to know all these concepts. And they translate into real-world performance. So I said this assembly class is really, really important. Even if you're just going to be a C++ programmer the rest of your life, you have to understand what's going on behind the hood so that when your boss is like, dude, you're getting page faults crazy, you're like, am I playing tennis? Like, what? Huh? What? You know? So, yeah. So that's why this class is so important. Are you going to be a professional assembly programmer? Maybe. It's good to have in your pocket, I guess. Probably not, though. But understanding how all this stuff works, yeah, it makes you a much better programmer. Much better. And then we will end that here today. If there's any questions, I will hang out and answer the questions for you guys. Otherwise, I will see you guys on Tuesday. Get the midterm done. Starts now. And the programming assignment is due on Saturday at midnight. Okay. All right. Thanks, guys. Peace out.